There's a star 4.24 light years from Earth. That number gets repeated so often in science communication that it has lost its ability to land. 4.24 light years. It sounds almost close. It is the closest star to our sun. It has a planet. That planet sits inside the zone where liquid water could theoretically exist on a surface. For nearly a decade, a significant portion of the popular science world has been pointing at the planet and calling it humanity's nearest hope. James Webb just looked at it properly for the first time, and what it saw does not match the story you were told. Not because the scientists were lying, not because the data was wrong, but because the gap between what the paper said and what the headlines repeated has been growing for years. And Webb's instruments have now made the polite version of this story very difficult to keep telling. The telescope does not read press releases. It reads photons. And the photons coming back from the direction of Proxima Centauri are telling a specific, measurable, uncomfortable story about what it is actually like in that neighborhood. Tonight, I want to give you that story unedited. Not the version that ends with possibility and wonder, and an invitation to dream. The version that ends with the data. Let's start with the star itself, because the marketing around red dwarfs has been nearly as misleading as the marketing around their planets. The public impression of a red dwarf is something gentle, smaller than our sun, cooler, dimmer, a quieter kind of light. That impression is almost perfectly backward. Proxima Centauri is an M-class red dwarf. Its mass is about 12% of our sun's. Its surface temperature is roughly 3,000 Kelvin compared to our sun's 5,178. It is genuinely smaller and dimmer. All of that is accurate. What gets left out is the interior structure, because the interior structure changes everything. Our sun has a radiative zone and a convective zone separated by a distinct boundary. The outer layers churn. The deep interior does not. The magnetic fields that generate solar weather are produced in the region where those two zones meet. Proxima Centauri does not have this structure. It is fully convective from core to surface. The entire star churns like a boiling pot. That churning tangles. Magnetic field lines throughout the star, not just at the surface boundary. And when field lines tangle under that kind of pressure, they snap. And when they snap, the energy released is enormous. In March 2016, astronomers recorded a single flare from Proxima Centauri that increased the star's brightness by a factor of 68 in the ultraviolet within seconds. Not 68%, 68 times. In 2019, a separate observation caught another event more than 100 times more energetic than any solar flare recorded in the modern instrumental record. And these are not rare exceptions. Researchers observing Proxima Centauri for 50 continuous hours detected 463 individual flare events during that window. That is nearly 10 per hour. That is not weather. That is climate. The violence is not the exception. The violence is the baseline. Now translate that into what it means for the planet sitting in that star's habitable zone. Proxima B orbits its star at a distance of roughly 0.0485 astronomical units. 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles. Proxima B sits at less than 5% of that distance from its star. It has to be that close because the star is so dim. To receive enough heat for liquid water to theoretically exist on a surface, the planet needs to be practically inside the star's atmosphere compared to our own orbital distance from the Sun. Being that close means two things that cannot be separated. The first is warmth. The second is everything else. At that distance, the stellar wind from Proxima Centauri hits Proxima B with a flux estimated by multiple independent research teams at somewhere between 1,000 and 2,000 times the flux Earth receives from our Sun. During a flare, which again happens roughly 10 times per hour on average, that flux spikes by factors that dwarf anything our own planet's shielding has ever had to handle. The extreme ultraviolet radiation alone, during a Proxima flare, arrives at Proxima B at levels hundreds of times higher than what Earth receives from the Sun during its most active periods. And that ultraviolet does something very specific to an atmosphere. A NASA study published in the Astrophysical Journal Letters took Earth's atmosphere, the actual composition and density of the air we breathe, and modeled what would happen to it if it were sitting where Proxima B sits, orbiting Proxima Centauri. The result was unambiguous. Earth's atmosphere would not survive on a geological timescale. The extreme ultraviolet radiation ionizes atmospheric gases. When a molecule is ionized, its electrons gain enough energy to escape the planet's gravity. As those negatively charged electrons leave, they pull positively charged ions along with them through electrostatic attraction. Not just hydrogen, the lightest element, but over time, heavier elements too. Oxygen, nitrogen. The molecules that make an atmosphere breathable. The model concluded that even heavier atmospheric components would be stripped away far faster under Proxima Centauri's radiation environment than anything our Sun has ever subjected Earth to. That study was published in 2017. The academic community knew what it implied almost immediately. The headline version of the story did not change. There is another mechanism that gets even less attention than atmospheric stripping, and it is arguably more fundamental. To sit in the habitable zone of a red dwarf, a planet has to orbit so close that gravitational tides lock it. The same side of the planet faces the star permanently. The other side faces away permanently. This is not a minor inconvenience. Tidal locking almost certainly destroys the internal mechanism that generates a global magnetic field. Here is why the magnetic field matters more than almost anything else in this conversation. Earth's magnetosphere is invisible. Every human being who has ever lived has spent their entire existence inside it without registering its presence. It deflects. The solar wind. It channels charged particles toward the poles, where they discharge harmlessly as auroras. It is the reason our planet has kept its atmosphere for 4.5 billion years under a star that, while much calmer than Proxima Centauri, still produces energetic events capable of disrupting technology here on Earth. Take the magnetosphere away, and the atmosphere becomes unprotected cargo. We have already watched this happen in our own solar system. Mars once had an atmosphere thick enough to support liquid water on its surface. Mars once had a magnetic field generated by a churning molten interior. Roughly 4 billion years ago, that interior cooled. The dynamo faltered. The field weakened and eventually died. The solar wind from our own comparatively quiet sun began peeling the Martian atmosphere off molecule by molecule. NASA's MAVEN spacecraft measured that process directly. It is still happening. Mars lost everything it needed to be habitable because it lost the shield that held it together. And our sun is a calm star by any objective comparison with Proxima Centauri. The magnetic field on Earth is generated by the planet's rotation combined with its liquid iron core. Tidal locking slows or stops that rotation. Slow rotation means a weak or absent global dynamo. No dynamo means no global field. No global field means no magnetosphere. No magnetosphere means nothing standing between the surface and one of the most violently active stars within 4 light years of our planet. Modeling by multiple independent teams, including work by Rebus and colleagues published in the years following Proxima B's discovery, consistently reached the conclusion that the planet has almost certainly lost most or all of its primordial atmosphere to stellar wind stripping. The academic record on this point has been walking in one direction for nearly a decade. The popular record has not followed. This is where the Webb data becomes important as a new layer on top of that existing picture. The telescope cannot yet image Proxima B directly at the resolution needed for atmospheric spectroscopy. The planet is simply too small, too close to its star, and our instruments are not quite there for this particular target. What Webb has done is begin to establish what the environment surrounding that star actually looks like at infrared sensitivity levels no previous telescope could achieve, and to establish what the pattern of rocky planet atmospheric retention looks like around red dwarf stars as a class. That second point is where the data has become genuinely significant. Webb has now looked carefully at several of the most high-profile rocky planet candidates around red dwarf stars. TRAPPIST-1b, the innermost planet of the TRAPPIST-1 system around a red dwarf star 40 light-years from Earth, showed no evidence of a thick atmosphere in Webb's 2023 thermal emission observations. The planet's dayside temperature matched what you would calculate for a bare rock with no atmosphere redistributing heat. TRAPPIST-1c, the second planet in that system and one sitting closer to the habitable zone, reached the same result in follow-up observations. LHS 3844b, a rocky planet studied by earlier missions, showed a bare rock signature with no atmosphere detectable. GJ 486b produced an ambiguous water vapor signal that subsequent analysis could not cleanly separate from contamination by water in the star's own atmosphere. Each of these planets was, at the time of its discovery, described in press materials using language that positioned it as a promising candidate. Each one, on closer examination with better instruments, has come back with the same failure mode. A pattern is emerging from the data. The pattern is not the one the optimistic framing predicted. Now it is fair to acknowledge that this does not prove no rocky planet around any red dwarf retains an atmosphere. Science does not work by the logic of universal exclusion from a small sample. Some researchers have proposed that planets around red dwarfs might replenish their atmospheres through volcanic outgassing faster than they are stripped. Some have modeled scenarios where a sufficiently dense atmosphere could survive under extreme stellar flux if the initial endowment was large enough. In May 2026, a study found tentative evidence of star-planet magnetic interaction at both Proxima B and Proxima D, which some researchers interpreted as a possible sign that these planets retain magnetic fields despite tidal locking, potentially through mechanisms not fully captured by existing models. Now, these are legitimate scientific possibilities. They are not endorsements of the version of the story you were sold. The version you were sold was that Proxima B is a candidate backup Earth. That framing moved through the press pipeline in 2016 and has never fully left. What the academic literature said in the papers underlying those press releases was more careful. It said the planet is rocky. It said the planet orbits inside the theoretical habitable zone. It said the stellar environment poses serious challenges to atmospheric retention and habitability. Those qualifications were present in the science. They did not survive the trip to the headline. This matters because it illustrates a structural problem in how space science reaches the public. Original papers are written in precise language. Press releases translate that language for a general audience and, in doing so, make choices about which qualifiers to carry forward and which to leave behind. News outlets receive the press releases and translate them again. Social media receives the news articles and translates them one final time. At each stage of that chain, the incentive runs toward the optimistic framing. Optimism generates engagement. Engagement generates traffic. Traffic is what the pipeline measures as success. The qualifier that changes the meaning of the entire claim is the one most likely to get dropped. The result is that a viewer who has been following space news for a decade has been told, in various forms and on multiple occasions, that we keep finding planets that could be like Earth. They have rarely been told what the follow-up papers concluded about each of those planets. And they have almost never been told that the follow-up papers, picture of planetary habitability that is considerably harder than the introductory version implied. It is also worth spending time on the distance, because 4.224 light years is one of those numbers that sounds manageable until you stay with it properly. The distance from Earth to the Sun is approximately 93 million miles. Proxima Centauri is 4.24 light years away. 1 light year is roughly 588 trillion miles, which means Proxima Centauri sits approximately 24.9 trillion miles from Earth. That is the distance from Earth to the Sun multiplied by roughly 268,000. Voyager 1 is the fastest human-made object ever to leave our solar system. It is currently moving at approximately 38,000 miles per hour. At that speed, it would take Voyager 1 roughly 75,000 years to reach Proxima Centauri. Every human civilization that has ever left a physical record of its existence, stacked end-to-end in time, would not fill that journey. The entire span of recorded human history is approximately 5,000 years. You would need to repeat it 15 times to cover the travel time, and Voyager 1 is not aimed at Proxima Centauri. Nothing we have ever launched is aimed at Proxima Centauri. The most ambitious proposed solution to this is the Breakthrough Starshot Initiative, which has suggested accelerating extremely thin light sails to roughly 20% of the speed of light using powerful ground-based lasers. At that velocity, a probe could reach the Alpha Centauri system in approximately 20 years. The fine print on that proposal includes the fact that a grain of dust hitting the sail at 20% of light speed carries the kinetic energy of a small explosive. It includes the fact that nothing capable of carrying a human being or a meaningful instrument package or a return propulsion system can be made small enough to be accelerated to that velocity with any laser array conceivable with current engineering. The proposal, in its most honest description, is a tiny camera on a tiny sail sent on a one-way trip that would produce a brief snapshot. It is not a mission in any sense that the word has historically carried. Chemical propulsion cannot bridge this distance on any human timescale. Ion propulsion cannot bridge it. Fusion propulsion, which remains theoretical as a working spacecraft engine, would require energy control we do not have. Antimatter. Propulsion could theoretically do it if we could manufacture antimatter at rates trillions of times higher than currently possible and store it indefinitely, which we cannot. The distance to Proxima Centauri is not a longer version of the distance to Mars. It is a categorically different class of problem, and our civilization currently has no working answer to it. Consider for a moment what that communication delay means even in the most optimistic scenario. A radio signal from a probe at Proxima Centauri takes 4.24 years to reach Earth. The reply takes another 4.24 years to return. A single round-trip exchange, one message and one response, takes 8.5 years. On Mars, where the signal delay peaks at about 24 minutes, NASA already has to build substantial autonomous decision-making into its rovers because 24 minutes is too long to wait for real-time guidance in an emergency. At Proxima Centauri, the communication delay is not measured in minutes. It is measured in the length of a human pregnancy, times approximately 9. There is no resupply architecture for a Proxima mission. There is no rescue architecture. There is no emergency return corridor. When something goes wrong in a mission to Proxima Centauri, the crew handles it alone with whatever they brought. Whatever they cannot fix, they accept the consequences of. The isolation does not operate as a hazard alongside the mission. It operates as the defining condition of the mission, from the moment the crew leaves to the moment the mission ends in whatever form it ends. This is the full picture that has been sitting underneath the popular framing of Proxima B for a decade. A star that is among the most violently active in our neighborhood. A radiation environment that multiple independent models agree would strip an Earth-like atmosphere far faster than it could be replenished through ordinary geological processes. A planet that is almost certainly tidally locked, removing the rotation that generates the dynamo that generates the field that is the primary reason Earth has kept its atmosphere. A distance so large that no human being alive today, and very likely no human being living in the next several generations, will see a probe reach it. And a body of follow-up research in the peer-reviewed literature that has been steadily downgrading the habitability case for years, while the popular version of the story has remained largely unchanged. Webb did not invent this picture. It inherited it, and is now adding to it with the only kind of data that actually settles arguments in this field: direct measurement. The pattern across rocky planets, orbiting red dwarf stars, is becoming clearer with each new observing run. It is not the pattern the optimistic model predicted. There is something important to sit with at the end of all of this. The popular story about Proxima B was never a malicious lie. The scientists doing the work wrote accurate papers. The details were present in the journals. What happened in the space between the journal and the viewer was a series of small translations, each one nudging the framing toward hope and away from the yes. Qualifiers, because hope is what the communication pipeline rewards and qualifiers are what it loses. The consequence of that pipeline is a public that has been given a comfortable story about the abundance of habitable worlds within reach, when the honest version of the story is more difficult. The nearest star is not a gentle neighbor. Its nearest planet is almost certainly not a candidate backup for this one. And the distance between here and there is not a challenge waiting to be solved by the next generation of rockets. It is a wall that our physics currently has no tool to pass through on any timescale that matters to the people alive today. That is not a reason for despair. It is a reason for accuracy. If we have been assuming that options exist beyond this planet on any relevant timescale, and the evidence keeps pushing back against that assumption, then the accurate response is to update the assumption, not to keep repeating the comfortable version until the data becomes too obvious to ignore. Webb's infrared readings do not lie. The photons that came back from the direction of Proxima Centauri recorded the truth of that environment without editorial judgment. What they showed is a star in a state of constant violence. A radiation environment that shreds the theoretical case for surface habitability on its nearest planet, and a rocky planet class around red dwarf stars that, case after case, keeps failing the atmospheric retention test when examined honestly. That is what the telescope saw. That is what the science says. And the gap between that and the version printed in the headlines is something worth understanding clearly. Because what fills that gap is not just a miscommunication. It is a decade of public belief built on a foundation the evidence has been eroding the entire time. The nearest star is not a doorway. The data says it is a warning. And the planet we were sold as a backup is not a backup. It is a reminder that the shelter we are already standing in is the one we have been treating as replaceable. It is not replaceable. Webb just confirmed it, one photon at a time. And there is one more piece of this worth naming before we close, because it tends to get swallowed by the larger argument. The TRAPPIST-1 system, which became the secondary target of all the habitability optimism once its 7 rocky planets were announced in 2017, is facing the same reckoning. TRAPPIST-1 is also a red dwarf. Its planets also orbit close. They are also likely tidally locked. And Webb has now looked at 2 of them carefully enough to draw a conclusion. And both conclusions point in the same direction as every other rocky world around every other red dwarf that has received genuine follow-up scrutiny. The atmospheric retention problem is not unique to Proxima B. It appears to be a structural feature of the entire category of world that was supposed to be common enough to fill the galaxy with options. The Drake equation, the famous back-of-envelope calculation of how many communicating civilizations might share the Milky Way, is only as useful as the numbers plugged into it. For years, those numbers were generated in an environment of limited data, and the honest response to limited data is generosity. Assume the best until you have evidence otherwise. The fraction of stars with planets, put it high. The data supports it. The fraction of those planets in the habitable zone, put it moderately high. The orbital statistics suggest plenty of candidates. The fraction of habitable zone planets that actually retain habitable conditions, this is where the data was thin, so generosity ruled. Now the data is getting less thin, and the number that generosity was applied to most, freely, is the one that Webb's observations are now beginning to measure directly. And the measured values are not the generous ones. None of this means the universe is empty. None of this means life does not exist elsewhere. It means the specific story we were given about the abundance and accessibility of habitable worlds, near enough and similar enough to matter on any human timescale, is more fragile than it was presented. The window is narrower. The conditions are harder to meet. The distance is more final. And the planet that was supposed to anchor the optimistic case is sitting inside one of the most hostile radiation environments within 4 light years of Earth. Almost certainly without the shield, it would need to hold an atmosphere against the star it orbits. That is the honest summary. That is what the data, accumulated across years of follow-up research and now sharpened by the most sensitive infrared telescope humanity has ever launched, is adding up to. Webb did not create this picture. It is completing it. And a picture that is complete is more useful than one that is comfortable, even when comfortable was easier to carry.